All right, let's dive right into one of the weirdest, most fascinating questions in all of quantum physics. Do virtual particles actually exist? Now, this sounds like it's straight out of science fiction, but the answer, well, it tells us something incredibly profound about reality itself. So I want you to think about this for a second. Right now, in what looks like the empty space all around you, are there countless, invisible little particles just blinking into and out of existence faster than you could ever imagine? And this is where it gets really interesting, because the debate over the answer actually tells us a ton about how science really works at the deepest levels. This is not going to be a simple yes or no. It's really a journey into what reality even means and how we try to describe it. Okay, so to get our heads around this, let's start with the first side of the debate. This is the skeptical argument, the one that says, hey, these virtual particles, they're really just a clever mathematical trick. So, from this point of view, a virtual particle isn't a thing you could ever touch or see. It's, well, it's a placeholder. It's a term that physicists pop into an equation. It's a concept they use in quantum field theory, the big theory that describes all the fundamental forces, just to make their math work out when they're trying to predict how real particles are going to interact. And this quote it nails the skeptical case, doesn't it? It basically says that confusing the math tool with an actual physical thing is a fundamental mistake. Quantum field theory is awesome because its predictions are spot on, not because it gives us a nice, neat little picture of what's happening behind the cosmic curtain. So the bottom line for the skeptics is this. Virtual particles are a convenient fiction. They're these handy little tools that help smooth over some really gnarly mathematical problems, like these infinities that would otherwise pop up and make all the calculations totally useless. And here's the wild part. They don't have to follow the normal rules of physics at all. They can have imaginary mass, they can appear to travel faster than light. They're basically physics outlaws. For the skeptic, what really matters is the final measurable result, not the mathematical gymnastics you use to get there. But, and this is a huge but, if it's all just a trick, why in the world does it work so unbelievably well? And that brings us to the counter-argument, that this so-called trick might just be the single most successful idea in the entire history of science. This is the core of the dilemma. You see, without the idea of virtual particles, some of the most important calculations in physics they completely fall apart. They spit out answers like infinity, which is basically the universe giving you a big red error message. But the moment you put virtual particles into those same equations, you get predictions that are just mind-blowingly accurate. And we're not talking about some abstract ideas here. No, these are real things we can go out and measure in a lab. You've got the Casimir effect. That's a literal physical force that pushes two metal plates together in a vacuum, seemingly from nowhere. Or the Lamb shift, a tiny but totally observable change in a hydrogen atom's energy. Or-best theories can only explain these things if they account for the effects of virtual particles. So that leads to the big question, right? Just how good are these predictions? Are we talking, in the ballpark, or are we talking about something else entirely? Oh, it is something else entirely. For one of these predictions, the magnetic properties of the electron, the theory matches what we measure in the real world to an accuracy of 99.999999999%. That is it's an absolutely staggering level of precision. I mean, to really wrap your head around that number, think of it like this. That's like measuring the entire continent of North America from one coast to the other and getting the distance right to within the width of a single human hair. A mathematical trick that can pull that off? Well, it's clearly describing something deeply, profoundly true about how our universe works. Okay, so we have these two really powerful arguments, right? On one hand, virtual particles seem like a mathematical fiction. On the other, they're the secret sauce in the most accurate theory we have ever dreamed up. So where do physicists actually land on this today? The modern consensus is this really beautiful blend of both views. Physicists today pretty much agree that virtual particles are, in fact, mathematical abstractions. They are an incredibly powerful and totally indispensable tool for doing calculations, but, and this is key, they're not fundamental independent things that you could ever, say, catch in a bottle. And they got to this conclusion through a really logical process. First, they said, okay, let's admit these things only exist as a concept inside the math of our theory. Second, they realized that, hey, without them, the math completely breaks. And third, this is the real kicker. They saw that using this mathematical tool gets them predictions that match up with reality with just unbelievable precision.
So you see what happened? The whole conversation shifted. The question changed from, are they real, to how incredibly useful are they for describing reality? So no, they may not be real in the same way a chair or a planet is real, but they are an absolutely essential part of our most successful description of reality. And this, of course, leads us to the final, biggest, most mind-bending question of all. This whole debate forces us to take a step back and ask something that sounds super simple but is anything but. What this whole thing really shows us is how science actually works when we're pushing at the absolute edges of what we know. Down at the quantum level, you can't just look and see what's going on. It doesn't work that way. Instead, what we do is build these abstract mathematical models that predict the things we can measure. At these frontiers of physics, the reality of a concept is basically judged by its success. The fact that the model works so incredibly well is the most powerful argument that it's a valid way to describe the universe. Its reality is its usefulness.
And so that's the final thought I want to leave you with. If our best, most successful, most precise description of the entire universe relies on concepts that aren't real in the way we usually think of that word, then what does real even mean anymore? It's a question that pulls us right out of physics and into philosophy, and honestly, that's what makes this whole thing so endlessly cool to think about.